It's time for another warm-up review. Let's get going. Label the following diagram of the circle of Willis. Good anatomy here. First we have letter A. That's going to be the anterior cerebral artery. Letter B is going to be the anterior communicating artery. C is the middle cerebral artery. D is the internal carotid artery. E is the posterior communicating artery. F is the posterior cerebral artery. G is the superior cerebellar artery. H is the basilar artery. I is the anterior inferior cerebellar artery. J is the vertebral artery. K is the PICA, the posterior inferior cerebellar artery. And L is the anterior spinal artery. All right, that's it for the warm-up. Let's get to the lecture now.
In this video, we're going to talk about pharmacokinetics and enzyme kinetics. Now, this isn't necessarily clinically relevant, and most students don't find it particularly exciting. But this is very high yield for step one. Now, I'm going to focus on what's most important for your exam, so make sure you really understand pharmacokinetics and pharmacodynamics really well. Let's start with enzyme kinetics, which is at least a 4, maybe a 5-star topic. You should expect at least one question on enzyme kinetics, Km, and Vmax, maybe several questions. Students often tell us you need to know Km and Vmax like the back of your hand for step one. Let's start with Michaelis-Menten kinetics. Say you have an enzyme that catalyzes some reaction, and you mix some of that enzyme with the substrate, which is S, and you measure the velocity of that reaction. Well, this graph shows you how the reaction velocity changes as the concentration of substrate changes. So the x-axis is the concentration of substrate, and the y-axis is the reaction velocity. So the first thing to notice is that down here, as the substrate concentration increases, the reaction velocity increases. More substrate leads to faster reactions. We call this first-order velocity, where the reaction velocity is directly proportional to the concentration of substrate. But as you continue to add more and more substrate, eventually you're going to saturate the enzyme. And once that enzyme gets saturated, you can't make the reaction go any faster no matter how much substrate you add. So up here, the enzyme is completely saturated and the reaction velocity reaches a plateau. We call this zero-order velocity or zero-order kinetics because the velocity is completely independent of the substrate concentration. It doesn't matter if you've got 1,000 particles of the substrate or 1,000,000 particles. If there are only enough enzyme binding sites for 100 particles, the velocity of the reaction is going to be the same. And we call this maximum reaction velocity Vmax. That's the maximum velocity that the reaction can achieve. If you wanted to speed up the reaction, how would you do it? Well, the enzyme is saturated, so the only way to speed things up would be to add more enzyme. Now, if you add more enzyme, you have more binding sites, and that shifts the whole graph up some, and Vmax is a little higher. So ultimately, Vmax is proportional to the amount of enzyme that's available. Okay, so what's Km? Km is called the Michaelis constant, but that name isn't really important. What is important is that you know that Km is a substrate concentration. Specifically, it's the concentration of substrate that gets your reaction to half of Vmax. It's the amount of substrate that's required for the enzyme to achieve half of the maximum velocity that that enzyme can achieve. So Km is a substrate concentration. If you look at this graph, you would say this is Vmax, and when half of Vmax is here, halfway between Vmax and 0. Then wherever that half Vmax is, you follow that out horizontally to intersect the graph, then drop down vertically to the x-axis, and whatever that concentration is, that's Km. So Km is the substrate concentration at 1/2 of Vmax. It's really pretty straightforward. Now, Km is determined by the enzyme's affinity for its substrate. If the enzyme has higher affinity for the substrate, the reaction gets to Vmax very quickly, and the slope of the graph is steeper, so Km will be lower. So a lower Km means that the enzyme has higher affinity for the substrate. It doesn't take as much substrate to get to half Vmax. Now let's look at this a different way. This is called a Lineweaver-Burke plot. It's the same data, but it's plotted on different axes. In a Lineweaver-Burke plot, the x-axis is 1 over S, 1 over the substrate concentration. And the y-axis is 1 over V, 1 over the reaction velocity. And what that does is kind of straighten out the curve. Now, the 3 points you have to know about this, and I really think you just have to memorize it because there's no great way to reason it out, but the 3 points to memorize are the slope of this graph, the x-intercept, and the y-intercept. So the slope of a Lineweaver-Burk plot is Km over Vmax. The x-intercept is the point where the graph crosses the x-axis, and that's 1 over minus Km. And the y-intercept is 1 over Vmax. Now, we mentioned that in a reaction that's reached Vmax and all the enzyme sites are saturated, the only way to speed up the reaction, or to raise Vmax, is to add more enzyme. So when you add more enzyme and increase Vmax, this graph flattens out. Vmax is higher, the y-intercept is lower, and the slope is lower. But Km hasn't changed, because we said Km is related to the enzyme's affinity for the substrate. Changing the enzyme concentration doesn't really change the enzyme's affinity for the substrate. Increasing the y-intercept means you have a lower Vmax because it's inversely proportional. And the further to the right the x-intercept is, the greater the Km. So you need to understand how a change to Vmax or Km is going to affect a Lineweaver-Burk plot. Now let's talk about what happens to Vmax and Km when you add an inhibitor, either a competitive inhibitor or a non-competitive inhibitor. Normally, a substrate binds to the active site of the enzyme, and the enzyme catalyzes some reaction. A competitive inhibitor is a substance that prevents the substrate from binding to the active site of the enzyme. This is usually because the inhibitor resembles the substrate, and the inhibitor binds directly to the active site. It competes for the active site. But if you give enough substrate, you can dilute out that competitive inhibitor so that it's basically irrelevant. So competitive inhibitors can be overcome by increasing the amount of substrate. A non-competitive inhibitor is a substance that changes the three-dimensional conformation of the enzyme so that even though the substrate can still bind to the active site, the enzyme activity is reduced. That three-dimensional conformation is crucial for normal protein function. Usually, non-competitive inhibitors bind to the enzyme allosterically, meaning they bind at some site other than the normal substrate binding site. But the important thing, in terms of enzyme kinetics, is that you cannot dilute out a non-competitive inhibitor by adding more substrate. So how do inhibitors affect our enzyme kinetics graphs? Well, a competitive inhibitor does not change Vmax. You can still achieve that same maximum velocity eventually if you give enough substrate. So with a competitive inhibitor, the Michaelis-Menten curve is shifted to the right. It takes a higher substrate concentration to reach Vmax, but Vmax doesn't change. With a non-competitive inhibitor, you cannot overcome the inhibition by giving more substrate. At some point, you're going to saturate the available enzyme and reach zero order velocity. And what you'll find is that when you reach that plateau, the Vmax is lower. So non-competitive inhibition will decrease Vmax, but it does not change Km. Now, what does that look like on a Lineweaver-Burk plot? Here, the yellow line represents the uninhibited enzyme. Now, when you add a competitive inhibitor, does that affect the Vmax? Competitive inhibitors do not change Vmax. Vmax is related to the enzyme concentration. So if a competitive inhibitor does not change Vmax, that means the y-intercept doesn't change. But it does change your x-intercept, which means Km is changing. A competitive inhibitor increases Km because Km is the substrate concentration at half Vmax. It takes more substrate to get to half Vmax with a competitive inhibitor on board. What about a non-competitive inhibitor? A non-competitive inhibitor decreases enzyme activity and reduces Vmax, but it does not change Km. So with a non-competitive inhibitor, the x-intercept doesn't change, but the y-intercept is going up, and that means a lower Vmax. So a non-competitive inhibitor decreases Vmax. Let's take a second and practice these. In your study guide, we have some unlabeled graphs, first without inhibitors and then with inhibitors. So I want you to pause the video and try to label these graphs, and then we'll talk through the answers together. On the Michaelis-Menten graph, A is Vmax, B is 1/2 Vmax, and then C is Km, which is the concentration of substrate needed to achieve 1/2 Vmax. D is indicating the region of first order velocity, and E is indicating the region of zero order velocity. And on the Lineweaver-Burk plot, F is 1 over minus Km, and G is 1 over Vmax. You're probably just going to have to memorize those two. Then on the graphs with the inhibitors, A is a competitive inhibitor, where you're increasing Km, but Vmax is unchanged. And B is a non-competitive inhibitor, where Vmax is decreased. Then on the Lineweaver-Burk plot, C is a non-competitive inhibitor, where Vmax is lower, so the y-intercept is moved up. And D is a competitive inhibitor, where you're changing Km. Let's go over some basic pharmacokinetic calculations. And again, this is hugely high yield. I know these equations can be intimidating, and some of this you just have to memorize so that you can just plug in the numbers into the equations. Fortunately, there are only 4 pharmacokinetic equations that you need to know. You should be able to answer all the calculation questions on your exam with just these 4 equations. And there's a page in your study guide where you can write down these 4 equations as we go through them. The first equation is the volume of distribution equals the amount of drug in the IV form divided by the concentration of the drug in the plasma. So that's VD equals D over C. And we say the IV form because basically we're factoring out bioavailability. When you give a drug IV, it's 100% bioavailable. So volume of distribution is the amount of drug given divided by the plasma concentration of the drug. The second equation deals with clearance. Clearance is the rate of elimination of a drug divided by the plasma drug concentration. Clearance is also equal to 0.7 times the volume of distribution divided by the half-life of the drug. And that's the equation you should probably memorize. Another way you can remember that is that clearance is K times the volume of distribution. So K is the elimination constant. And these 2 equations together tell us that K is 0.7 divided by the half-life. So clearance is equal to the elimination constant times the volume of distribution, where the elimination constant is 0.7 divided by the half-life. The third equation is a loading dose. Loading dose is equal to the concentration at steady state times the volume of distribution. So what's the concentration at steady state? Well, that's your desired concentration, your target concentration. You're giving a drug, and you know you have to get it up to a certain plasma concentration where it's going to have the desired effect. So to determine the loading dose, you need to decide what your desired concentration is, and then multiply that by the volume of distribution. And then the fourth equation is the equation for maintenance dose. Once you've got the drug up to that desired concentration, you have to keep giving a dose every day or every 8 hours or whatever it might be in order to maintain that steady state concentration. So the equation for maintenance dose is the steady state concentration times the clearance. So those are the 4 equations you definitely need to know for your test: volume of distribution, clearance, loading dose, and maintenance dose. Make sure you memorize those equations. Now, the best way to show you how to use these equations is to work through some questions, plugging in the numbers, which we're going to do in the end of session quiz. These equations are a great example of what we call a marker board topic. When you go into the testing center to take step 1, after you've checked in and you sit down at your computer station, they're going to give you a marker board and a dry erase marker. The marker board is just a couple of sheets of paper that have been laminated. And we recommend that the first thing you do as soon as your first block starts is to spend just a couple of minutes writing down some equations and facts so you can move through the test quickly. Now, if you look at the very last page of the DIT study guide, you're going to find some test day tips, which we'll talk about later on in the course. And on that page is a short list of some recommended marker board topics, which includes these 4 pharmacokinetic equations. That way, when you get a question about pharmacokinetics later on in the exam, you don't have to panic. You just start plugging in the numbers. So make sure you have these equations memorized and you can write them down accurately and quickly. If you practice writing them down 1 time every day between now and your test, you're guaranteed to have them locked in. Now, one other thing to be aware of when you're calculating loading dose and maintenance dose is bioavailability. Bioavailability takes into account the fact that a lot of the time when you take a drug orally, you only absorb some of the drug. All the drug doesn't actually get into the blood. Most oral drugs have bioavailability less than 100%. So sometimes you'll see an equation that says loading dose equals the concentration at steady state times the volume of distribution divided by F, where F is the bioavailability. Well, the good news is that we've never heard of students having questions that ask you to adjust for bioavailability. So the question will either specifically say it's 100% bioavailable in oral form, or the question will say that the drug is given IV. So I think it's pretty safe to just forget about F when you're memorizing all these equations. Let's say a quick word about half-life. Half-life is the amount of time it takes to eliminate half of the drug that's in the body. And if you're infusing a drug at a constant rate, that drug is going to reach about 94% of the steady state concentration in approximately 4 half-lives. That's the number you want to know. 94% after 4 half-lives. So if you're infusing that drug constantly, it's going to hit 94% of steady state at 4 half-lives of the drug. And then it's also going to be eliminated in the same way. When you stop the infusion and let a patient sit for 4 half-lives, about 94% of the drug is going to be eliminated during that time. So it kind of goes both ways. So I would know these numbers. After 1 half-life, obviously you've eliminated 50% of the drug. At 2 half-lives, you eliminate 50% of whatever's left, which is another 25%. So now you've eliminated 75% of the starting amount. At 3 half-lives, you've eliminated 87.5%. And at 4 half-lives, you've eliminated 94%. And again, those work the other way too. If If you're giving a drug, after 1 half-life, you've achieved 50% of the steady state concentration. After 2 half-lives, you've achieved 75% of steady state, and on up to 94% after 4 half-lives. And again, those numbers are worth knowing. So now we're ready to tackle the end-of-session quiz, which is going to focus entirely on doing calculations with our 4 pharmacokinetic equations. All these quiz questions deal with this scenario. A 60-kilogram man with status asthmaticus is being given an IV infusion of a drug X at 60 milligrams per hour. The clearance of drug X is 2 liters per hour, and the volume of distribution is approximately 0.5 liters per kilogram. 48 hours after administration has begun, the asthma attack is under control. At this time, the concentration of drug X in his plasma is 20 milligrams per liter. So go ahead and try to answer all these questions on your own, and then we'll work through them together. All right, the first question says, what's the half-life of drug X in this patient? So you start with the equation for clearance. Clearance equals 0.7 times the volume of distribution divided by the half-life. Then you switch that around and you get half-life equals 0.7 times the volume of distribution divided by the clearance. So to figure out the answer, you need the volume of distribution and you need the clearance. Well, the clearance was given. It said the clearance of drug X is 2 liters per hour. And the volume of distribution is kind of given. It says volume of distribution is 0.5 liters per kilogram, but liters per kilogram is not a unit for volume. Don't ignore the units in these problems. Volume is just liters, not liters per kilogram. So if this patient is 60 kilograms, the volume of distribution for this drug in this patient is 0.5 times 60, which gives you 30 liters. So the volume of distribution here is 30 liters, and you multiply that by 0.7 and divide by your clearance, which is 2, and you get 10.5. So the half-life here is 10.5 hours. Next, what loading dose could have been used to reach the target concentration of 20 milligrams per liter? So in order to calculate your loading dose, you take the target concentration of 20 milligrams per liter and multiply it by the volume of distribution, which you found was 30 liters, and you get a loading dose of 600 milligrams. Next, if the patient begins to show signs of toxicity and the target concentration is decreased to 10 milligrams per liter, what would you need to do to get to this level? So basically, you're cutting the target concentration in half. So how do we get to the new level? Well, you stop the infusion for just 1 half-life. That's the meaning of half-life. You stop the infusion for 1 half-life, which is 10.5 hours, and the plasma concentration will decrease by half. Next, assuming 100% bioavailability, and again, they're either going to have to tell you that the drug is 100% bioavailable, or they're going to have to say the drug is given IV. And if it's an IV drug, you're going to assume it's 100% bioavailable. So, assuming 100% bioavailability, what oral dose of drug X would be necessary to maintain the new target level? So this is looking for a maintenance dose. Maintenance dose is equal to the concentration at steady state times clearance. Our new concentration at steady state is 10 milligrams per liter. They gave us the clearance in the question. It's 2 liters per hour. So the maintenance dose is 20 milligrams per hour. And last one. If the patient has kidney disease and the clearance is reduced to 1 liter per hour, but the volume of distribution is unchanged, what effect will this have on loading dose and maintenance dose? So the loading dose is based upon the volume of distribution. And we're told that the volume of distribution is unchanged. So in this case, the loading dose does not change. But the maintenance dose is decreased because of the reduced clearance. So you have to decrease the maintenance dose, but you wouldn't change the loading dose. So that's it for now. I'll see you next time.